In this problem, we're asked for the Ka of H2PO4-. So it's important to recognize what Ka means. A Ka reaction is always acid hydrolysis. It can either be represented simply by an acid losing its proton, or in this case, we're going to write its reaction with water. So it's going to be H2PO4 minus plus H2O. And remember, since it's a weak acid, it's going to be an equilibrium reaction. And we're going to protonate the water. Classic acid hydrolysis. And we're going to end up with the conjugate base HPO4 2-. So if we look through, choice B is the one that matches that. Also, a ribbon is not a symbol in chemistry. So if you ever see that, you can automatically eliminate that choice. In this problem, we're presented with a titration of 50 milliliters of 0.5 molar methylamine with 1 molar HCl. Anytime we add in a strong acid or strong base to a solution, when in doubt, ISF it out. Yes, that's right, we're going to be doing yet another ICF table. Because strong things react to completion. So, now, we need to remember that ICF tables use moles. So I'm just going to solve for the moles of both of the things that we're using here. We've got 0.5 molar methylamine. And we're multiplying that by 0.05 liters, 50 milliliters. So this is going to give us a total of 0.025 mole of methylamine. We'll do the same thing then with the HCl. So the HCl is 1 molar. And remember, it doesn't matter which strong acid we use. It's just the source of H plus times 0.0125 liters. And that's going to equal 0.0125 moles. So those of you at home might be saying, wait a minute, this is a half equivalence point problem. If you recognize that, you can instantly plug in 2 pH equals pKa. Perfectly fine. But here, let's just do the whole ICF table. You know what? Why not? So, I'm going to plug in our values. 0.025 moles here. And this is going to be 0.0125. On the other side, 0. Identify our limiting reagent. So minus 0.0125 minus 0.0125 and plus 0.0125 to give us 0.0125, 0, and 0.0125 moles once it's all said and done. Wait a minute. A weak base. Its conjugate weak acid. Both remaining. Look at what we've got. It's a buffer. And what a buffer it is. Which means we can go straight to our friend Henderson Hasselbach. So recall, Henderson Hasselbach is pH is equal to pKa plus the log of base divided by acid. It can be in any units, as long as they're the same. And just note, here we're given a Kb. So the easiest way to go about this will be to just solve for Ka first. So I'm going to use Ka times the Kb that we were given, 4.2 times 10 to the negative fourth is equal to Kw, which at 25 degrees Celsius is 1 times 10 to the negative 14th. So we'll divide each side by the Kb. we'll end up getting that the Ka that we're going to use for this problem is equal to 2.38 times 10 to the negative 11th. Now that we have our Ka, let's figure out what our pH is, shall we? So, pH will be equal to the negative log of the Ka we just solved for, 2.38 times 10 to the negative 11th, plus the log of, and again, as long as we have the similar units, or the same units rather. So I'm just going to plug in the number of moles. No need to solve for molarity. And you might be noticing something, again, pretty cool here. Any number divided by itself is 1, and the log of 1 is simply 0. So this part cancels out, and we get pH is equal to pKa. So when we take this negative log, we'll end up getting that the pH is equal to 10.62. So this next question is all about what's appropriate in terms of an indicator change. So just note, you want your indicator to change color during the either spike or plummet of a pH change, because in the middle of that spike or plummet is where we find our equivalence point. So here I just did an arbitrary titration of a weak acid with a strong base. Note that the equivalence point happens to be above 7. We would want our indicator to change colors at some point within this range here. So we'd want it to change somewhere between here and here. So I just picked an arbitrary one that maybe be red at a lower pH and yellow at a higher pH. So let's just go through each of these choices. The indicator pKa should be within 1 pH unit of the pH at the endpoint of the titration. Well, the endpoint is the equivalence point, and if the pK of the indicator, the pKa of the indicator is where it changes colors, because remember, indicators are just acid bases. If the pKa is within 1 of the endpoint, it's going to be in that vertical jump, so I like this choice. The indicator should change color within the vertical jump in pH. Oh yeah, absolutely, that's what we just said. The indicator should have an acid form and a base form that are different colors. Well, if they don't change colors, well then you're not really going to be able to tell when you hit the endpoint, so I like that one too. The indicator should not react with components of the titration. You don't want a side reaction going on, you just want to know where the equivalence point is. And then finally, the indicator should be polyprotic. Oh no, if it's polyprotic, that means there's lots of different forms. That's not really a consideration here. So, choice E ends up being the answer because that's the one that's false. So maybe I shouldn't have crossed that out. False. This last question here is a little bit of a throwback. It wants us to solve for the delta G of an acid-base reaction with a few given parameters. Okay, so here are our equations from thermodynamics that are going to be useful here. First, we need to find a delta G standard. We need to find some way of relating this information to thermo. And remember, we can relate equilibrium constants by using this equation here. So, I'm going to write delta G standard is equal to negative R 0.008314 kilojoules per mole Kelvin times T. This is, the problem should have specified at 298 K. Times the natural log of our K value. And remember, Ka is just a form of equilibrium constant, so we can just plug this in. 1.8 times 10 to the negative fifth. When we do that, we'll end up getting that delta G standard equals 27.1 kilojoules per mole. Notice that that's very positive, which makes sense because these weak acid associations are not very favorable. It's a pretty small Ka, therefore the reactants would be favored, therefore delta G standard should be positive. But wait a minute, are we under standard conditions? Standard conditions would mean 1 molar of everything, and that most assuredly is not the case, which means we're going to need to do a subsequent calculation to get delta G from delta G standard, and that's where this equation is going to come into play. First, just to make this a little bit easier for myself, I'm going to take this in a piecemeal approach. I'm going to solve for Q. So Q, remember, is products over reactants. So our acid dissociation is acetic acid, CH3, COOH, dissociating into H+, and acetate, CH3, COO-. So Q is just going to be products over reactants, as it always is. H+ times CH3, COO-, all divided by CH3COOH. So we're not explicitly given the H+ concentration, but we can find it using the pH. Remember that pH means the negative log of the H+ concentration is equal to 4 here. So I'm going to move the negative sign to that side and do 10 to both powers. And that's going to end up giving us that the H+ concentration is equal to 1 times 10 to the -4th. Now we have all the concentrations we need to solve for Q. So let's do just that. This is going to equal 1 times 10 to the -4th times acetate's concentration, 2 times 10 to the -4th, all divided by 1. So this is going to equal 2 times 10 to the -8th. There we have our Q, and now we can plug in to this equation up here. So delta G is going to equal our delta G standard, 27.1 kilojoules per mole, plus R, 0.008314 kilojoules per mole Kelvin. Again, this problem should have specified that it's at 298 K. Times the natural log of that Q that we solved for before. 2 times 10 to the -8. So we'll end up getting delta G is equal to 27.1 kilojoules per mole plus, and this whole thing here ends up being negative 43.9 kilojoules per mole. So our delta G ends up being negative 16.8 kilojoules per mole. So while this acid dissociation is not favorable under standard conditions, with such a small value for Q, we still may need to make some more products. So this would indeed go forward. Okay, everybody. Well, that is practice exam 2B. I hope that your preparations are coming along well, and hope you're ready to dominate that exam. Keep up the hard work.